So if you go to Canvas under the modules for this week, you'll be able to see we've got 4 example problems. So here we've got just some different configurations here of some columns, beams, and decking. And then example 4 is on a separate handout under the module, and will be a little bit more complicated configuration for load tracing. So we're going to work our way up to example 4. All right. So load tracing is one of the more important things. I would argue one of the most important things that we cover in Structures 1. Really, load tracing is one of those things that once it clicks, I think it makes good sense, but until it does, it can be hard to really understand how the loads move through a structure. Conceptually, I think it's pretty simple. We can look at a configuration like this and understand that the loads start at the top of the structure and they end up in the ground. But the challenge is figuring out that load path, okay, and then tracing those loads through each of the structural elements. So let's start out like we typically do and define what load tracing is. Okay, so your textbook is going to go into some detailed definition for load tracing. But here, I'm going to simplify this as the systematic process of determining loads and support reactions for individual structural members. Okay, so the systematic process of determining loads. Okay, typically we'll be given loads at the top of the structure and maybe some self weights, but we'll have to accumulate those loads and add them up through the structure. So we'll find those loads and the support reactions. Of individual structural members. Okay, so the important thing to remember here is we're going to start at the uppermost building element and work our way down through the foundation. Okay, so an example structure, okay, might include roof. So typically the roof is where we would start our load tracing. Going to joist, going to beams, to columns, down to the foundation. Okay, so different structures may have different combinations of larger structural elements, and so it's up to us to determine what that load path looks like. Okay, so these will include dead loads. Okay, we've covered dead loads, you know, in great detail already, but you know, fixed equipment, the structure itself. Okay, and basically any permanent items. Okay, load tracing also includes live loads. So sometimes we need to handle dead loads and live loads differently. But again, live loads are going to be people, furnishings, okay, movable items. Right, so load tracing is going to involve figuring out the dead loads and live loads that are placed on the structure and tracing those loads throughout the structure, all the way to the foundation, ultimately to the ground. The important thing to remember here is that in general, the shorter the load path is, the more efficient the structure is. Okay, so that's it in general. A shorter load path is a more efficient structure. Right, so what we mean here by a more efficient structure, okay, the shorter the load path is, that means the less structural elements are involved. And so the fewer structural elements that we have means a more economical structure. Okay, so the shorter the load path means that there are fewer structural elements, which means that our structure is more economical. Right, when we complete a load tracing problem or exercise, there are some terms that we need to know, okay? And some of these terms may be familiar to you. If they're not, that's okay. We're going to get familiar with them. The first here is what we call tributary area. So when we complete a load tracing problem, we need to understand the tributary area as the area that we apply to a particular structural member when we're doing our calculation. So this concept considers the area that a member must support as being halfway between adjacent similar members. Okay, so the area that a member must support is halfway between adjacent similar members. Okay, adjacent similar members. Okay, so I'm going to show you guys kind of what that means in a second. For now, we'll just define it and then we'll look at it schematically. Okay, related to tributary area, we have what we call tributary width. Okay, essentially the tributary width is what's going to determine our tributary area. Okay, so our tributary width is the distance between adjacent similar members. Okay, so it's the distance between the member that we're looking at and the adjacent similar members. Okay, so let's look at what this adjacent similar members really means. All right, so let's just take a very simple example here of a series of beams. So let's say we're looking at a plan view of a structure and we're looking in particular at 3 beams here. All right, so let's call these B1, B2, and B3. All right, let's just say that these beams are 10 foot long. Okay, so again, we're looking at the length of the beams here is being 10 feet. And we'll say that they are spaced 5 foot on center. Okay, so 5 foot from the center of B1 to the center of B2, and 5 foot from the center of B2 to the center of B3. Okay, so what we're doing here is we're taking kind of what's probably a larger structure here and just taking part of it out so that we can define these terms here for tributary area and tributary width. All right, let's say that we want to look at B2. Okay, so we want to know what is the tributary area of beam B2 and what is the tributary width, okay, for B2. All right, so tributary width, we said, is the distance between that element and adjacent similar members. So the tributary width for B2 would go halfway over to B1. So halfway here would be 2.5 feet. Okay, so there's 5 foot between B1 and B2, so 2.5 feet of that width would be attributed here to B2. The rest would count towards B1's tributary width. And also between B2 and B3, we want to go halfway there. Okay, so another 2.5 feet here would give us our tributary width between B2 and B3. So our tributary width for B2 extends 2.5 feet to the left and 2.5 feet to the right in this plan view. So that's a tributary width of 5 feet here. Okay, so if we look at B2, our tributary width is 5 feet. Okay, our tributary area, okay, is the area that's applied to B2. So that's going to be our width times the length of the beam. Okay, so we're looking for the area on top of B2. So 5 feet times our length of 10 feet. So we'd have a tributary area of 50 square feet. All right, so let's look at B1 and B3 here. So this was B2. So if we look at B1, okay, again, assuming that we've taken a simplified structure here, B1 and B3 are the end beams. So there are no beams to the left of B1, no beams to the right of B3 on this plan view. Then we would have tributary width here of 2.5 feet for B1. So this whole area, okay, highlighted here, would go to B1. So the tributary width for B1 is 2.5 feet. And if we look at B3 would go halfway back to B2. Okay, so that tributary width is also going to be 2.5 feet. Okay, so I think the hardest thing about load tracing problems is visualizing. Well, we typically have a 2D plan view of a structure or part of a structure, and we try to visualize this in 3 dimensions, right? So when we do this load tracing, if we're looking again at B2, our goal is to take B2 and figure out what part of the structure above that beam is being supported by that beam. So in this case, we've got 5 feet of width and we have a length of beam of 10 feet. So that tells us about the area that's supported. Okay. And we know that beams B1 and B3 are supporting a smaller area. Okay. So if we were to calculate those tributary areas for these two, it's supporting half of the width here. So 2.5 feet times the same length of 10 feet gives us 25 square feet. Okay. So half of the width here corresponds to half of the tributary area that's being supported. So in theory, if you think about how we would size these beams, okay, in theory, we could size the outer beams a little bit smaller than this interior beam B2. Okay, any questions so far? All right, let's take a look at this first example here, example 1. All right, so here we have a wood flooring framing system, and we're given the uniform deck load on the wood flooring, okay? So what we have here is a series of deck boards, okay? So it's a wood flooring, so the best thing to probably picture here would be like a back deck on a house or something like that, where you have a series of decking boards here. And then these boards are connected to these beams, okay, below. So we're given the span length here of beams 16 feet. They're 4 foot on center. Okay, and we're given the deck boards above. Okay, so for this, we want to find the load on each of these beams, A, B, C, and D. So let's take this 3-dimensional sketch here and translate this where we draw these beams. We're trying to find the load on the beams. So let's sketch these beams here in plan view. So this is load tracing example 1. Okay, so what we know about these beams is that they're 16 foot long, they're spaced 4 foot on center, and there's 4 of them total, A, B, C, and D. So we'll sketch those just like we did on the previous example. Try to show them about the same distance apart. Okay, so we've got A, B, C, and D. All right, again, we know that these beams are 16 foot in length. So we'll note that here. And we know that they're 4 foot apart on center. So there's 4 feet between each of these beams. To show that. So 4 foot on center. Okay, we also know, because we're told in the problem statement, that the uniform deck load is 50 pounds per square foot. Okay, so we're basically given the load on this area. Okay, so this basically all of this decking, we know that there's 50 pounds of weight per square foot of this decking if we apply that as one unit here. So 50 pounds per square foot is the uniform load for the decking. Okay, and again, we're asked to find the load on each of these beams, A, B, C, and D. All right, so the first thing that we want to do is look at the tributary widths for each of them. All right, so for beam A, 2.5 feet, 2 feet from A halfway over to B, 2 feet over to B, right? So there's a 4 foot span here. So 2 foot of that span will go to A, and 2 foot of that span will go to B. Okay, so here, if we want to use color, uniform load will be applied over a 2 foot span for beam A. Beam B, we've got 2 foot halfway over to A, halfway to C, we've got another 2 feet. Okay, so our uniform load will be applied over a 4 foot span here at B. Let's use a different color here for B. Okay, C has got a 2 foot span to the left, 2 foot span to the right here. So I'll use a different color even here. Okay, and then D, being an end one, we've got 2 foot here back to C. So that's got a 2 foot tributary width. All right, so we can see here that beam A has a 2 foot tributary width. Beam C has a 2 foot tributary width. So we're going to simplify our calculations a little bit here. Just tally up our tributary widths. Okay, we know A is 2 feet. D is 2 feet. Okay, so typically the end beams will have, unless the spacing is different, okay, when the spacing is uniform like this, 4 foot on center, then our end beams will have the same tributary width and our interior beams will have the same tributary width. So here, A and D, our end beams are 2 feet. Our interior beams, B and C, 2 foot on either side. So tributary width for B is 4 feet, 2 plus 2. Tributary width for C, 2 plus 2, 4 feet. So B is 4 feet and C is 4 feet. Okay, so now this is where it gets to be not really hard, but it can be a little bit tricky to visualize how this is working, okay? All right, so what we've done here is we've calculated our tributary widths. Okay, so given the layout that we have here, given that we have 4 foot between each of these beams, and there's a uniform deck load of 50 pounds per square foot on these beams, we now want to translate this to each of the beams. Okay, so that's going to be done based on the tributary width. So we can look first at beams A and D, since those have similar or the same tributary widths. Beam A and beam D has a 2 foot tributary width. Okay, so if we draw or sketch those beams here, okay, this is beam A and D. We're given that the uniform load from the decking is 50 pounds per square foot. We're going to take that load and apply it to each of these beams based on the tributary width. Okay, so to get our uniform load on the beam, we take our decking load here, 50 pounds per square foot of area, and we're going to multiply that by our tributary width, 2 feet. Okay, so we're given this load per area, and we take this load per area based on this area here. Okay, so again, this pink shading here represents 50 pounds per square foot. And we're going to figure out how that translates specifically to the beam by multiplying it by our tributary width here of 2 feet. So that gives us 100 pounds per foot for our uniform loading on that beam. So what that's telling us is that, just like we've looked at beams before, okay, we have this uniform load on beam A, and it's going to equal the uniform load on beam D, since they have the same width here, tributary width of 2 feet. And so this is equal to 100 pounds per foot. Okay, so again, trying to visualize how this is going through the structure, we've got 50 pounds per square feet of area on the entire system here of beams. And that translates based on a 2 foot tributary width to 100 pounds per foot of length along beam A and along beam D, since they're equal. Okay, on this example, we're just asked to find, okay, the load on each of these beams. So this is the load on beam A and the load on beam D. In future problems, we're going to be asked to trace the load all the way through the structure. So in essence, if this problem were expanded to include the entire system, if this were a decking system like we mentioned, there would be some sort of columns holding this in place. So in the future, what we're going to be looking for are these column reactions on the end. So we'll typically name these C1 and C2 or something like that, to represent the columns that are there supporting these beams. Again, for this one, we're not asked to do that. For this one, we're just asked to find this value here. Any questions about this problem so far? All right, so that was beam A and beam D, which represents the end beams in this system. Okay, beam B and C also share a tributary width here of 4 feet. So next we'll look at B and C and calculate that uniform load. Beam B equals beam C. And that was a 4-foot tributary width. Okay, so that gives us a uniform load. Okay, when we're going from load on a certain area down to load on a beam or a girder that's a uniformly distributed load like this, we'll always take our given load, okay, 50 pounds per square foot in this case, multiply that by our tributary width, 4 foot in this case. Okay, so this is going to give us a uniform load of 200 pounds per foot. Okay, so if we sketch this beam, okay, this is beam B, which is equal to beam C. So it has a uniform load here of 200 pounds per foot, which is double A and D. Okay, again, that's what we're asked to find in this problem. Okay, this is the uniform load on B and the uniform load on C, since they have the same tributary width. And in the future, we'll be looking to find these support reactions here, which represent columns. So C1 and C2. Any questions about this problem? All right, let's take a look at example 2 now. All right, so example 2 is going to look a little bit similar. Okay, but we're asked now to trace the load a little bit further through this structure. Okay, so here we want to trace the loads on the planks, on the beams, and on the columns. All right, so now instead of given the uniform load on the entire decking system, we're asked to actually calculate the uniform load on the planks, given the load that will be placed on top of this deck, okay? So we're given that the load on the deck itself is 60 PSF live load, 8 PSF dead load from the weight of the deck itself. So that's 68 PSF, okay, that we'll use to trace the load. So this is example 2. Okay, I had a question, what is tributary area for? So So tributary area can sometimes be useful to know. For the most part, tributary width is going to tell us what we need to know, okay? The tributary area is the area that's attributed to a certain beam or another structural element, whereas the tributary width is just the width. But if we're given the loading above, then we don't necessarily have to calculate the area. But it is important to know and understand what that concept means. That's a good question. All right, example 2, load tracing. Okay, let's look again at what we're given and what we're asked to do. So here we're given the dead load and live load. They've already added those for us here, so 68 PSF. So our total load is 68 pounds per square foot. Okay, and we're asked here, trace the loads on the planks, the beams, and the columns. Okay, so the planks here, the beams here, 2 beams, and there are 1, 2, 3, 4 columns. All right, so we want to trace this loading here to the planks, then to the beams, and finally to the columns. All right, so we'll start with the planks. Again, we'll always start at the top of the structure and work our way down through the structure. So let's look first at the size of the planks, okay? So we're not explicitly given the width of the planks in the problem, but they're covering a distance of 12 feet here. We know that they have a length of 8 feet. They're covering a distance of 12 feet. So if we count these planks, 1, 2, 3, 4, you'll find that there are 12 planks, okay? So these planks are 1 foot wide. Okay, so note here, sometimes if it seems like we're not given all the information, we might have to dig a little bit further to find what we need. So we'll note here, okay, based on our sketch, okay, planks are 1 foot wide. Okay, so again, our planks are 12 foot, covered in 12-foot span, and there are 12 of them. So that means that each plank is 1 foot wide and each plank is 8 foot in length because we're given the length here of 8 feet. Okay, we also know, okay, that our planks are going to be supported by these beams. Okay, so our planks here are resting on one beam on the left end of our sketch, one beam on the right end of our sketch. So if we sketch this again in 2D here, we want to show beam on the left, we'll call this B1, beam on the right, B2. Okay, again, we're not given that this is B1 and B2, we're just going to name them. And each of these beams is supporting a series of planks. Okay, so that's my attempt at plan view. Okay, so we got a beam on the left, beam on the right, a series of planks. So going into this page, we've got 11 more planks there on these beams. So our plank loading, okay, we're given they're supporting a 68 PSF load, 68 pounds per square foot. The tributary width for each plank, if they're spaced at 1 foot on center, the tributary width will be 1 foot to the left, 1 foot to the right. That won't necessarily be the case for the end planks, but let's just simplify this problem and apply it to all of them. So 1 foot. So that gives us 68 pounds per foot for our plank loading. So again, what we're taking here is we're taking the given loading from the weight of these planks plus the weight of whatever we're putting on top of this deck. And we translate that into a plank loading of 68 pounds per foot of length here. Knowing that they're supported on each end, B1 and B2. We know that there'll be a reaction here. Reaction at B1. And a reaction here at B2. And we're looking at a length here of 8 feet. Okay, so each plank is 8 foot long, which means that the distance between the beams is 8 feet. So we'll note that here. All right, based on what we've done so far in class, just a few weeks ago and what we just covered on the test just now, we've got a uniform loading on a beam, and we're trying to find the support reactions, right? That's essentially what this problem is. When we have a simplified problem like this, where we have just a rectangular uniform loading, no point loads, no triangular loads, we can simplify our calculations for the support reactions, okay? So basically a shortcut formula, if you will. Okay, so let's make a note here. If we have a simply supported beam or girder, okay, and on that, we have one rectangular uniform load. Okay, one single rectangular with no point loads. No other loads. Okay, we can simplify our support calculations. Okay, so that simplified formula here okay, our support reaction, we'll call R, is going to be equal to W times L over 2. Okay, so anytime we have a situation where we have a simply supported beam or girder, okay, so in other words, one support on either end, we have a uniform loading that's rectangular in nature over the entire length of the beam, and we know what that is, okay, no other point loads or other loads at all, we can calculate those support reactions by WL over 2, okay, only if this criteria is applied. So what this will do is just save you a little bit of time in your calculations. So for this example, okay, if we want to apply this, okay, we've got our support reactions here, B1, okay, is equal to B2. Okay, so in this case, we can make a note here, R1 is equal to R2, okay, equals R. So if we have this criteria, then the support on the left side of the beam or girder will be equal to the support reaction on the right side. So B1 equals B2 equals WL over 2. Okay, so our W here that we calculated, 68 pounds per foot, times the length of beam, 8 feet, divided by 2, okay? So all this is simplifying based on what you really already know. So basically, if we have a uniform load like this with no other point loads and everything symmetrical, then you know that half of that load will be attributed to one support, half the load will be attributed to the other support. So that's where we get this equation. Okay, so if we do this math, we get 272 pounds. Okay, so the reaction at B1 equals the reaction at B2 equals 272 pounds. Okay, so that represents the reaction between the planks and the beams. Any questions on that? All right, let's look now at the planks. We looked at the plank to beam. Let's look now at the beam to column. Okay, so we found the uniform load along each plank. We took that, calculated the load at the reaction between each plank and each of these beams. Now we want to look at the beam to column. So we've got two beams, each supported by two columns. Okay, since this is symmetrical, we know that basically what's happening on this side will also be happening on this side. So let's take a look at one of those beams. All right. So we named these earlier B1 and B2. Okay, we found out that the support reactions between the planks and the columns were equal. So in other words, the uniform loading on B1 will equal the uniform loading on B2. So B1 and B2 are going to be equal essentially. Okay, what we found here is that the reaction between each plank and each beam was 272 pounds. So let's zoom in here. Okay, so plank to beam, 272 pounds. So this beam is 12 foot long. There's 12 planks. We know that each plank is 1 foot in length. So for every 1 foot of length, there's 272 pounds. Okay. So our W here, 272 pounds for every foot of length, right? That's what we found here. So for every 1 foot of length along each of these beams, there was a point load essentially of 272 pounds. So we'll sketch that here. Uniform load is 272 pounds per foot. Okay, each of these beams are supported by 2 columns. Okay, so we've got columns C1 and C2, we'll just call them that. C1 and C2 reactions. Okay, so we can find those using that same formula we just mentioned. Okay, so we've got a uniform load acting on the entire length of beam. Okay, we also know that each beam is 12 foot in length. So we can show that here. Okay, so C1 equals C2 equals WL over 2. Okay, so our W here, 272 pounds per foot. Acting over a length of 12 feet. Divided by 2. So that gives us 1,632 pounds. Okay, so the reaction between each column, C1 and C2, with each of those beams is 1,632 pounds, 1.63 kips. Any questions about that?
So is that how you write the answer to the problem? Or you just put in the structure elements in that column?
That's right. So yeah, that's a good question. So basically, it's going to depend on what we're asked for. So for this one, we're asked to trace the loads on the planks, beams, and columns. So what we did is we started with the planks, and we had to get that uniform load to get the support reaction. So typically what we're looking to show are those support reactions. So the loads in between. So to get these support reactions at the beams, we could then use that to find the support reactions at the columns. So typically what we're looking for to kind of show as our answer is a couple of things really. So the first important thing is going to be the uniform loadings at each spot. And then the second thing is that support reaction. So if you want to highlight or show this uniform load, that's key. If you don't have that, then you can't find the support reaction. So that's a great question.
Okay, so you don't have to like put it on a diagram per se, as long as you have it like written and.
That's right. Yeah, no, that's a good question too. So basically, the way I typically do it, and for this problem, you don't really have to put it on a diagram or really show it. When we get into some more complicated or I guess larger structures, what we'll do is I'll go through and I will actually write B1, B2, and then I'll name each of the columns. So basically, most of the time, it'll be up to us individually to sort of label everything so that we can track it. And that's another way to really understand the structure, is recognizing here that there are two beams. So labeling each of those beams. Also recognizing in this case that this is very symmetrical. So we could call both of these B1. It's a typical beam. So we could call them both B1 knowing that they're the same.